Good morning and good afternoon, good evening. My name is Ioannis Panetas. I'm a senior scientific advisor at FlowJo Informatics, which is part of BD Biosciences. And today we're going to be talking about compensation and unmixing. Those are very closely matching terms, right? They're very similar. We're going to be discussing about what makes them so different and why we have different terms for the same thing. So I will introduce you to the concept of compensation and unmixing and why it is essential to do it in our analysis and for our data analysis. I will show you methods we can use in order to compensate depending of different types of data we might have. For example, as we said already, traditional data or spectral data. And then I will show you, of course, everything will be centralized around FlowJo version 11 and specifically version 11.1, where I will highlight also how everything works out within version 11 with a demo. So getting started, just to summarize the agenda here, let me use a laser pointer somewhere here. Okay, the topics we're gonna touch ground is, first of all, I want to show you a very short theory behind compensation and unmixing and why we need it in flow cytometry. So for all of those of you that are really new to flow cytometry, I want to highlight why we need compensation and unmixing to analyze our data. Second, I will present to you the new compensation platform. It's a very updated platform for version 11 and what makes it much superior than previous version and more user-friendly. And I will highlight all the processes that are happening the moment you initiate the compensation platform step by step, how FlowJo create gates, create size gates, how it gates positive and negative within each single stain controls, and so forth. And finally, we're going to jump into FlowJo version 11 and see how it all works out in different data sets. So feel free at any time point to type in the chat box your questions or in the Q&A. I think we don't have a Q&A box, but we have the chat box, and feel free to use it to ask your question, and I will make sure to monitor at each every few minutes. Right, let's start with the challenge. The challenge we're dealing in flow cytometry. So in flow, we will use fluorescent probes attached to monoclonal antibodies against cell antigens. And that's what you're seeing here on the left. So you see a cell, and we used in that case FITC, which is conjugated to CD3 or CD3 conjugated to FITC. And we can use this antibody in order to detect CD3 in our samples. Yeah, so here you can see it highlighted with green. So once now this sample is acquired from our instrument, our cytometer or our sorter, it will be excited to emit light. Yeah, so the cytometer, so it's just the, okay, you see here the emission. Every cell passing through the cytometer will be excited by the blue laser here, and it will emit here, you see in the green histogram, it will emit light, which is represented here. Yeah. So the instrument on the other side will detect that emission. So in that case, you see those rectangles are the detectors of the instrument. And once detected, then we can really identify CD3 positive T cells by looking here the intensity of FITC, which would translate later on, of course, in CD3 antigen density. So this is how with the monoclonal antibody in flow cytometry, we can identify CD3 antigen density on specific subsets or cells. Now, one of the goals in flow, of course, is to be able, it's not enough to have one antibody and just detect CD3 in our sample. In flow cytometry, the goal is to be able to detect multiple antigens on the same exact cell by staining with multiple fluorescent probes. Okay, so taking here as an example, we have CD3 fits, and CD19PE. Yeah, so those will be bound into different kinds of cells, as you see. And of course, while passing through the cytometer once again, those will emit in slightly different wavelengths, but they also overlap somehow. Yeah, so now what you see is that the cells that bound CD3 and emit here in that wavelength, the green one, some of this emission of CD3 spills into a non-primary detector. So it spills into the detector that is used to detect CD19. And that's the problem we're dealing in flow cytometry. Yeah? So now instead of the ideal analysis that we should be able to do to identify CD19 and CD3 positive T cells or P cells, now we're seeing something like that in reality. Yeah? So some of our CD3 positive T cells actually spill over into the CD19 channel, and they appear as double positive, which is of course not true biology behind it, but as the result of this spectral overlap of the Fiji emission into the PE detector. Okay, so of course it's not done there. Our experiment is not ruined. But we can apply something compensation in order to fix that issue. Okay, so another example here, you can appreciate this time those two different dyes. Okay, both fluorochromes which emit to each other detectors. So in that case, it's even worse. So you can see both emissions from each antibody used here spill over to each other. Yeah, so to the detector of each other. So we would actually have populations that are double positive for both cases. So now here, both CD19 and CD3, okay, those two populations appear double positive. So looking at this, um, uh, we have two double positive population, which does not correspond to through biology. And of course, I cannot do anything in FlowJo with that, right? So I cannot really gate on those populations, thinking that those are double positive populations. And also I cannot extract statistics. I cannot do anything downstream. So we need to fix that through the process of compensation. So what applying compensation means? Okay, it's basically determining how much signal from each fluorochrome is measured by the rest of the detectors. So how much P is detected from the secondary detector and vice versa for all the rest detectors of the instrument, and then applying math behind that in order to subtract the signal out and result to something like this, where we have CD19 single positive and CD3 single positive populations here without any overlap or fake double positive populations. Okay, so basically, if you think of it in a different, more artistic way, applying compensation or unmixing is basically going from something that we see on the left here into something from the right. So you can think of it as when we have um, basically a colorful painting with all the colors mixed up together. We need to go back into the contribution of each individual color that made this painting. And this is how we need to instruct our cytometer or sorter in order to be able to detect all those single colors accurately so that we have the true biology through data analysis. Okay. That was just a very short introduction here. We have some more, of course. How can we do that, though? Yeah, so what do we need to have in our experiment in order to be able to instruct the cytometer how to recognize its different fluorochrome? So for the compensation, we would need the so-called single stain controls or compensation controls. Those are used in order to instruct the instrument how to see its color and, of course, to calculate this spillover we mentioned before. Yeah. So basically, what we're going to do is we're going to use cells or bits, or even better, both, if you're using if you were using cells for your analysis. And then we will prepare samples. Okay, here you see all those single stain controls, which have only one fluorescent antibody within. Yeah, so they're stained each time with all the different colors, one by one. Okay, so here you see we have a panel of 15 approximately single stain controls. And for each one of those, okay, we have a different spectral emission. Okay, so the cytometer records all of those and then calculate the overlap and the spectral overlap between all of the detectors on the instruments we're using. Okay, so you see here we have different contributions. So some fluorochromes are spilling more. Okay, like here, for example, fluorochrome number 2 here, you see it emits to all other detectors too, but others are less problematic, like fluorochrome 3 here. You see we have mainly on the primary detector, but we also have very little signal in other detectors. Okay, so that's the very first step. And of course, we also never forget an unstained control of cells, beads, or both once again. Yeah, so this can be very useful if we want to determine autofluorescence or other uses to use it as the negative control in our compensation matrix. Okay, so now going from the spillover, the single stain controls, calculating the spillover, that's the first step we have done. And now we need to apply compensation. So don't be scared about the math behind it. So what actually happens in traditional compensation, when we say traditional, we simply mean each fluorochrome, okay, corresponds to one detector. Yeah, so that's traditional for us. So here we see three fluorochromes, fluorochrome 1, fluorochrome 2, and fluorochrome 3. So we just inverted here the histograms so that we see it in a different way. So we see the detectors as rows. So we have 3 detectors for 3 fluorochromes. That's the traditional way of compensation. So now what happens in the instrument? Detector 1 here has signal 100% from the fluorochrome 1 because we assigned it as the primary detector. Then we also have 15% from fluorochrome 2 and 1% from fluorochrome 3. Okay, so this is the problem here of the spectral spillover. So we have more signal in detector 1 that doesn't only come from the fluorochrome 1. Okay, so this is inverted now. It's written as a equation here. So all the signal of the detector 1, 2, 3, we assign the value of 1. So the 100% is 1 for the fluorochrome 1, 0,15 for the fluorochrome 2, and 0,01 for fluorochrome 3. Okay, so what we need to solve now is this equation. There is some very complex math behind it, I have to say. It's really tough to do it, of course, manually or on a piece of paper. That's why we do it algorithmic in FlowJo, which is much, much faster. So what we need to solve here is basically to detect how much fluorochrome 1 we have here. So we invert this spillover matrix. Okay, we invert that and that becomes our compensation matrix applied to our data. Okay, so this is the value that helps us determine how much of each fluorochrome we have. And something similar, very, very similar, it's not a completely different way, happens to the spectral unmixing, okay, instead of traditional, but the only difference is instead of having only 3 detectors to detect those fluorochromes, we have multiple detectors that we can use them. So we don't have any more a square matrix, but a rectangular matrix and a different and much more complex math. We're going to be talking about it a bit later on about spectrum. Okay. Right. So now, how does FlowJo version 11 simplifies all that? Okay, so I'll show you the steps so that you don't need to do all this math, all this gating, and we just need the single stain controls to begin with. Okay. Are there any questions in the meantime? I haven't checked the chat box. Okay, I can't see anything. So I'll just move on, right? So how can we do it in version 11.1? Okay, so this is just a screenshot of the compensation wizard in version 11.1, which is the latest version. And also I'll show you around. Okay, first step we need to do once we open a new workbench is, of course, we need to load our single stain controls. Yeah, so we talked a lot about single stain controls before. So now is where we need those. Of course, FlowJo can also recognize the matrix. Um, we can recognize the matrix that came from the instrument, the acquisition defined matrix, and you will see it down here. Yeah, under compensation matrices, you will see your acquisition defined matrix. And of course, in some instruments, this has been optimized. So you can use those instruments to have a really good compensation matrix. For example, for fax discover data, we have the spectral FX applied, which is also transferred in FlowJo. So ideally, you would use this for your these parameters for your gating. Yeah. Here I'm gonna show you, of course, how you can do everything from scratch in FlowJo, okay, and use our algorithms to do so. So first we will load our compensation data or single stain controls. So those should appear here. So under acquired data, you have compensation data, and you should see all your single stain controls here. Okay. The very first step that happens is FlowJo will create the size gate. So it's basically, it gates all your single stain controls so that they have similar autofluorescence within, so, or scattering intensities within, and assigns a positive and negative gate. So here, those you will see right here. Then above, you can switch between traditional and spectral. Again, traditional is what we said before. We use a primary detector for each fluorochrome. Okay, and we have the same number of detectors and fluorochromes or single stain controls. Spectral, we simply use all the wavelength and all detectors of our instrument if it's a spectral instrument. And the second button here is AutoSpill on and off. We're going to be talking about it later. The two different algorithms for compensating or unmixing. And below you will see the list of your single stain controls. So you see here, I have, for example, 8 single stain controls, and FlowJo will try to find which detector has the highest intensity for each single stain control and assign it to it. So here is where FlowJo automatically assigns a detector to each single stain control. Okay, and finally, negative and positive populations for each single stain control can be assigned right here. If now your sample is an unstained control, if you have an unstained control, unstained cells or bits, FlowJo will try to identify this through the name of the sample. And instead of having this colorful wheel here that you see, okay, you will have this gray, okay, this gray dot, which corresponds to an unstained control. Yeah, so gray would mean unstained control. So that's the overview of how it looks like, just a bit more dedicated into that topic. The size gate is created, so you will visualize it here under each one of your single stain controls. That's our size gate. You can, of course, modify it if you don't agree with how FlowJo gated. This is an automatic gate. And for each now single stain control, and the size gate, it will create a positive and negative gate. Okay, so you see here, it will you'll see it in the form of a histogram. It will place a gate for positive and negative, which you can use for the traditional algorithm for compensating. Okay, so that's all automatic processes the moment you click on the compensation wizard with single stain controls within. Okay. I see a question here. Thanks. May I know if it's not available in version 10? In version 10, I don't know, I probably saw this a bit too late, this as a question, so I don't know to what you're referring. But the compensation platform is, of course, we have the compensation wizard also in version 10. Yeah. And we do have the same algorithms in there. We have the traditional compensation, spectral, as well as AutoSpill and traditional algorithms, as we're going to see later. So all this is also possible in version 10. Okay, all this what I'm showing here. It's a bit optimized, as I'm going to show you a bit later. Optimize it in version 11, but you can of course do everything in version 10 as well. But in the next steps, you're going to see how in version 11 is a bit more optimal. Okay, I hope I answered your question. I didn't know what exactly was the topic, but I'm guessing you're referring to the compensation wizard. Okay. Now, the next step after we create those gates, where we have the size gate, positive and negative, then the spillover is calculated. What we said before, how much of its fluorescent prose is spilling into non-primary detectors. Okay, so FlowJo will try to do this automatically. Okay, so using your negative and positive gates within the size gate it created. And then after you press create matrix, FlowJo will create this matrix, apply to your data. And so, like in this case here, it will show you single population that have been compensated, and we don't have anymore this double spillover present anymore. Okay. Right. So the result, something happened here with the slide. The result is unmixed data, okay, and a rectangular matrix. Okay, so and that's because I'm gonna show it to you also later in the demo. We have one-to-one assignments, one detector and one fluorochrome. So we have a square matrix in that case. For the traditional data. So now what happens with spectral compensation or unmixing? All those processes I mentioned before are the same. So just some notes here. Spectral is referring, okay, when we use the full spectrum of the fluorescent signal, and our fluorescent probes are measured from all detectors of the instrument. So spectral instruments have been designed to have smaller detectors all across the wavelength, and they have a better coverage of the light. Okay, so we might have a two-color panel, and you can use it traditional way where you have two detectors, or you can measure those two fluorochromes over 78 or less detectors simultaneously. Okay. So of course, any cytometer can collect signal in all detectors. So you can simply use all of your detectors. It's not so optimized as with spectral data, but if you have a two-color panel and you have 8 detectors, you can still use more detectors than fluorochromes in your traditional cytometer. Okay. It's just the last step is the spectral cytometers are more optimized, as I said before. They do a very good job in splitting all the wavelength in very thin sections. Okay, and that way your unmixing or compensation would be a much better result in the end. Okay. See another question here. For size gating, should the gate be applied to all live cells or restricted only to singlets? For size gating, so so in FlowJo does that automatically. It creates this size gate, okay, with as you saw before. If you have beads, it will really use the portion of cells with similar scatters. So if we have many differences in the scatter intensities, this will be not inside this gate. So I suppose this process leads to less doublets because it's not going to use the same different scattering intensities that typically doublets would have. So it would isolate more or gate more singlets in that case. Now, if you want to do your size gating alone, like or replace the automatic gates from FlowJo, you can since those are, of course, single stain controls, we cannot have a live dead staining in there, of course not. But we can do a gate, an additional gate, in order to gate out the doublets and use this as our size gate if we think we have a lot of doublets. So what is recommended? Another question here, should we use only the detectors required for our fluorochromes or all available detectors? This is a very tough question to answer. If you have, I'm guessing you mentioned about the traditional cytometers where you don't have, not considered as spectral cytometer. Yes. So I think ideally you would do a test. If you, I would do this in cases that I have not a very good panel and I have a lot of spectral spillover to secondary channels. And if the compensation matrix is really bad, like then I would consider leaving all detectors in and see if this solves a little bit the resolution. Like if like you have a bad panel and you have less resolution and you cannot analyze your data, then of course this would be something to consider, to leave all detectors open and see if this solve of this equation produce a result that is better for your analysis. Yeah. So later on, we're going to talk a bit about some metrics like the spillover spread metrics and the total spread metrics that this can help you. You could do the same experiment, see how much spreading you have. And then if by keeping all your detectors open, you have less spreading, then this would be, yeah, my preference to use all the detectors open. Okay. Right. So we talked about this before. Once again here, the difference between traditional and spectral. Here we have one primary detector. You see great out in traditional, and then we have two secondary detectors, which are for the other two fluorochromes. However, in spectral, you see we have much more detectors, but only three fluorochromes that are detected through all those different detectors. So that's why it can be a better and more accurate solution of the compensation matrix and applied to your data. Okay, so the math simply is different. Okay, so we have much different math compared to the traditional. So instead of just reversing this matrix of spillover values here, we cannot do the same thing. But in that case, we do need to solve and find how much fluorochrome we have in this case. The math is different, it's more complex, and it's a different algorithm used for finding how much fluorochrome we have across all the spectrum of detectors used in this experiment. Okay. Okay. How does the spectral unmixing is used within FlowJo? So first of all, you need some spectral data. Okay. So you will load again. It's the same thing as with the traditional compensation. You will load your data under compensation data here. And then you will have spectral selected. So you select this button here, spectral. This is automatically on by default. And below you will see, and that's very helpful, already in version 11, you can see this spectral plot. What this plot shows is each one of your single stain controls selected here below, okay, across all of your detectors. So you can really see the signal and where your single stain control has the highest intensities. Okay, so you can scroll through the different single stain controls and see it for yourself. Then, again, the same process, we have this size gate automatically created and negative and positive gates for childs of this size gate. Here the main difference is that we don't have all detectors used here. So here we assign FlowJo assigns the detector with the highest intensity for that single stain control, but we do not use all of our detectors here, because you see here I have so many detectors, but only 16 colors. So that should not be, don't worry about that. When you have the spectral button checked here, FlowJo will use all of your detectors to unmix or compensate your data. Okay, and finally, the same thing, we still can use unstained controls. So you can unclick the colorful button here if you have an unstained control and use it, either for autofluorescence, unmixing, or other processes. Okay. Right. So let's talk now about the next algorithm, because so far we talked about FlowJo creating positive and negative gates, okay, for your size population. Yeah. If you're doing the traditional way of the traditional algorithm, you need to assign those positive and negative gates in order for FlowJo to calculate the compensation matrix. However, we do have as a default in version 11 the AutoSpill algorithm for calculating the compensation matrix, which basically it's a different algorithm. It's published in Nature. And basically what AutoSpill can do is you do not need to define a positive and a negative gate for each single stain controls. So the moment you click on AutoSpill on, as we're going to see later, you do not need anymore the positive and negative gates, because it calculates through linear regression. So it calculates all events in a line, okay, and it tries to compensate those out. Yeah, so it doesn't need only the positive and negative. It needs all the data, put them in a line, and then compensate those out. Okay. It has an iterative nature, meaning it calculates multiple times, not just a single time in a single solution. It calculates many times, and it's improving each time it's run through the algorithm. So the result might be even better than the traditional gating of positive and negative. And finally, it can also be used for unmixing the autofluorescence. If you have a unstained control, you can use it with the AutoSpill algorithm, and no problem, this will be unmixing out the autofluorescence from the rest of the detectors. So the effect is easier cytometry and much easier algorithm, especially if you have very large panels. AutoSpill runs very fast, meaning all the preparation of checking the positive and negative gates and all of this can take time. However, when you use AutoSpill, you don't need to define all that, so you can just avoid, save a lot of time and create a matrix which is very, it's identical in many cases as with the traditional algorithms. Okay. So no gates, okay, means that even if you have some faint single stain controls like this one, so you see we have not a clear distinction between positive and negative, AutoSpill can use those controls. Yeah, so there is no problem in there. So you can use even controls that have very few cells or very few positive, much easier than you would do in traditional compensation. Okay. So I see another question from Julia related to the previous question. How does the software calculate compensation with if we leave all detectors open, but the panel is smaller than the total number of detectors? We will not have single stain control for all fluorochrome, but only for those that are relevant to our analysis. So Julia, is just the same thing as I showed earlier. Okay, if you think of spectral, you have all those different detectors. Yeah. So all those different detectors are used to detect those three fluorochromes. Now, if here you had on the left-hand side, if you had on the traditional 8 detectors, let's say you had here 8 detectors, and then for 3 fluorochromes only, and you leave all detectors open, okay, you just acquire additional channels, okay, automatically, then you would not use the traditional compensation anymore. Yeah, so when you fit that to FlowJo, you would really check that box of spectral again, because it is spectral. If you think we have, it is spectral unmixing, we have more detectors than fluorochrome. So again, we cannot make this equation here because we don't have one-to-one, but we do need to do ordinary least squares or less unmixing. And in that case, you can still do it with traditional setup of data, but having more detectors. It's the math behind it is the same. We have more detectors than fluorochrome, so we can use the spectral algorithm. I hope that, okay, perfect. Okay. Right. So for the setup of AutoSpill, we will, by definition, in version 11, we have AutoSpill on because it's much faster and easier for our users to unmix or compensate without the need of positive and negative gates. So you need to keep AutoSpill on here. If you keep it off, then it's basically the traditional way of compensation where you need to assign positive and negative gates. Okay. Below, you will see automatically when you have AutoSpill on, you don't have those positive and negative gates anymore on your histograms here. So the algorithm will take in account all events within the size gates. Yeah, as we said before, it will put all those events, positive, negative, and everything in the middle in a line, and then those will be used for the calculations. And once again, if you have unstained controls, you can assign them here as unstained controls with a gray button and include it in or outside of the list of parameters to be used for compensation. Okay, so the computation is this. With AutoSpill, we again have the single stain controls. We have no positive and negative gates, so it will use all the data within this line. We calculate the spillover once again, and then we use that slope of this line basically to compensate the controls and invert this. Yeah, so we should have in the end compensated data. As I said, it's AutoSpill is much more robust, meaning events that are outliers outside of this line are weighted less, and that's an advantage. It's not going to take in consideration events that are much further for any reason outside of this line. So it will only weight more events that are on the line. Okay. And of course, it has iterative nature, so it will run once, twice, it will run multiple times to produce a new matrix, apply this matrix, and repeat till we have an acceptable result. So it's a very, very good algorithm. That's why we have implemented it as the default type of compensation or unmixing in FlowJo, version 11. Okay. Now, there has been a lot of discussion for autofluorescence and unmixing and how we can improve that, especially if you're working with difficult tissues like liver tissues or other kinds of tissues. How can we unmix the autofluorescence in a spectral instrument? So of course you can do that in many different instruments after you identify which channel is your most autofluorescent channel. You can do that in your instrument and assign this as an empty channel where you load your unstained control or your unstained cells in there. Yeah, the same thing we can do in FlowJo. Yeah, so either you have traditional or the spectral algorithm. You can use an extra control, okay, an extra unstained control, and assign it. So here you see, and assign it to a parameter that has to a detector that has the highest intensity. Yeah, so and that's a trick with having those spectral plots. You can see here. You can click on your unstained control, your unstained cells, and see where they have the highest intensity, in which detector. And then you can assign that detector, okay, on your unstained control. You can grade out here, as you see, or use it as a color control for the spectral unmixing. And then during the process of compensation, either spectral or traditional, the autofluorescence will be compensated out from the rest of the detectors. Yeah? So this will be seen also a bit later with a spectral dataset where I have an unstained control, and I'm going to show you how we can assign it as a single stain control. It's just treating it as an extra control. We treat autofluorescence as an exogenous dye, which we can we can check in the list of parameters and use it as normal, yeah, as it was an antibody in there. Okay. And the same again, once again for AutoSpill. So this was more for traditional data where you gray that out. And for AutoSpill, you use it again as a single stain control. You check it. And here we don't need any gates. Just this would be the only difference. And again, we can treat it to correct or to unmix the autofluorescence from our samples. Okay. Right. So, and just the last part before we go to the demo, I'm gonna show you some additional um, 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 outputs or metrics we can use in order to, have a look at our panel design or our instrument performance and some metrics that can show you how good our compensation was and if there's anything needed to be, if anything is needed to be improved. Sebastian, hi, have a question. Can more than one autofluorescent population be used to create a matrix, beads and bigger cells? Theoretically, yes. You can use multiple populations. So ideally, the setup would be the following here. You would have a spectral instrument in that case. You would identify, let's say you had, I don't know, neutrophils and monocytes or something like that. And those two can have, of course, very different autofluorescence. Okay, you identify those, and then ideally you would have a single stain control, or you would have two controls, two unstained controls, where the one control you would gate as a size gate your monocytes, and on the other you would gate your granulocytes. Yeah, I hope it makes sense. So you keep two additional channels, so it doesn't make any difference. You can use multiple autofluorescence signature, keep additional channels open, assign it to the most autofluorescence detector, and then unmix the data. So it is possible, yeah. I hope I got it right and I answered you right. If this can be done in FlowJo version 10 as well, yes, can be done in version 10 as well. But then, Sebastian, the problem, of course, would be um, which matrix, uh, if you apply one matrix, okay, and then you use the lymphocytes, or you get on the monocytes or granulocytes, then you accounted for both. So it would be the unmixing matrix would be somewhere in the middle in that case. Yeah. So maybe it would be better if you have a panel specifically only for monocytes, for example, to have only the autofluorescence of monocytes unmixed in that case. Alexis, hi, good evening. Is asking if unmixing done with weight optimization or not. In version 11, no, we don't have the weight optimization. Not yet. I don't know if it's in the scope. I'm not sure. But no, this is not used in that case. It's the typical spectral unmixing that we have in version 10 without the optimization. But it's a good idea, maybe if we could have it as the default to do. But of course, I know it computationally it takes a lot of effort to do this optimization. That's the only reasons I wouldn't mix in FlowJo. Okay, that's feedback accepted. Thank you. Right. Let's go to the metrics before we go to the demo. So the two metrics we can generate within FlowJo when unmixing is the spillover spread matrix and the total spread matrix. So those two metrics are calculated once you compensate within FlowJo. Yeah, so if you have an acquisition defined matrix, we don't have this available. Okay, so basically, about the spread. Okay, spread is the measure between the resolution of positive and negative, okay, in a pair of dies after compensation. So basically what happens here is if you have a high spillover to some secondary detectors, and we need a lot of subtractions from the rest of the channel, and this can lead to error. So this is typically an instrument error where now you see we have more deviation. So this is revealed after we compensate. You have this spread, okay, which can really make difficult then on your fully stained samples to identify the double positive population, because you see this spread here. If you put it in a panel and you have CD3, CD56 here, this spread would be preventing us for finding the double population easily. So then we need to make sure, we either have a different fluorochrome brightness or a different anti-density. So all those factors contribute to that spillover spread. Okay, so if you have lower brightness, it would give more spread. If you have lower antigen density as well, and higher spillover would also give more spread. But it, of course, has to do with the instrument performance and the way the detectors are detecting this fluorochrome we have assigned. So the spillover spread matrix, you will find it there as SSM. And this is normalized to the dye intensity. It's normalized to the brightness. Okay, so it's more of a measure of the instrument performance rather the panel design itself. So here we should avoid having values more than like we should have values less than 10 here. Yeah, so ideally you would have under like 5 or like low values um, in a good panel. You see anything like 10, it's worrying to market. Sorry, I just got disconnected. Can you confirm that you can see my screen and you can hear me? Okay, perfect. Sorry, I don't know what happened really. Um, so, okay, perfect. Thank you. So I was talking about the total spread, which is a different metric that you can calculate if you have the traditional algorithm. It's not available for the AutoSpill algorithm, and it's basically it doesn't normalize anymore to the MFI. Okay, so it's affected by how bright are specific fluorochromes, and the values are much different. So here you should be looking more at higher values that the heat map would saturate around 2000. Yeah, so you should look at lower values than that. Okay. Right, and the final metric we have is the spectral similarity. Okay, so basically it just shows you in values of 0 to 1 how dissimilar are two fluorochromes. So if you have two fluorochromes that are very non-similar, it would have a value of 0. Yeah, if you have very high similarity, or if two fluorochromes are identical, you would have a value of 1. So this is how you would get that metrics. All of those metrics are still available in version 10 to have to say, yeah. So we color them and the heat maps are adjusted to the range that we expect to have as a result of a panel. Okay. So just to summarize before we go to the demo, I hope I could convince you how important compensation is necessary in multicolor flow cytometry in order to calculate the antigen densities of its the antigen density on our cells and correctly phenotype. We have multiple different methods, which include traditional, spectral, and mixing, but also different algorithms that either require your positive and negative gates, or we have the AutoSpill algorithm that does not require any positive and negative gates. And finally, we do have some metrics that we can use for panel design and for ensuring proper compensation. So with this, I just want to spend the rest of the minutes just in a quick demo, okay, just to show you everything in FlowJo. Okay, I'll share my screen here. Okay, here we are. So I'll just open FlowJo 11. So this is 11.1. And I will open a new workbench. Okay, so here in the workbench, first of all, I will load some traditional data just to show you the setup. I load the data. So the FlowJo version 11 will automatically identify and add your single stain controls into your compensation data. So you see here, I have 12 single stain controls in the compensation data. And I do also get my acquisition defined matrix here. Okay, so if you want to see the matrix you would have in the instrument, you can visualize that here. Yeah, we also have some tools. It's not our recommendation in any case to correct. So you have the option here, you see, to edit the matrix. So it gives you a warning, like, are you sure you want to edit those values? You can really use this, press edit, and then you can manually input. But of course, we have no real guidelines on how to do that. Yeah, this is really subjective to the user at this point. Okay. Right, so if we want to do the compensation from scratch, I'll use my color controls here, my compensation data, and go to the compensation platform here on the left. Okay, then in the main window here, it tells you, okay, which group is used for the compensation. So here we have compensation data, and then I can select here next. Okay. So now FlowJo did already all those calculations. Okay, it created, as we said before, this size gate. Okay, for each one of our color controls. So I can go through my different samples here. We have in some cases cells, in some cases beads. Okay, and we also have, as you see here below, okay, we have some unstained control. So the unstained control, you can assign it just with a click of a button here. So this is stained control, this is unstained control. And the check means I use it for compensation or not. I use this single stain control for compensation or and not considering for the matrix. Okay. In addition, you see at the top, okay, those are traditional data. So it was not a spectral instrument. So we have, few detectors here, but you can still see the spectral plots just to approve that, okay, do I have in this single stain control higher intensity for Alexa floor 88? Of course I do. I see it here. Okay, so for the rest, I don't have much signal in there. Okay, so that's how you can look at those plots. If you want, you can hide this. In that case, we don't really need to have it here, and just use the size and positive and negative. So for the traditional algorithm, okay, like not using the AutoSpill, that's what I mean traditional, we need to assign a positive and a negative gate for each one of the single stain controls. So you see here, I would need to go for every sample. In cases that I haven't identified, I need to place a gate, submit it as the negative. Okay, that's the classic algorithm. Okay. And then I could press here, create matrix, and then that would be it. However, if I want to use my AutoSpill, okay, which is my default, and that's always my recommendation, you can click on here, AutoSpill on, and now the gates are not used. So you'll see here this message, gates unused in AutoSpill. Yeah, so we don't use, even if you have them or not have them here, they're not really used. Okay, so then in order to, once you assign here the correct detectors, detector assignment can be right here, okay, or here for every single stain control. Once I'm ready and happy with what I have, okay, I can press here, create matrix. Okay, can go here to preview, and then I can see my matrix. Okay. Ideally, I can do it also here. So you can see your matrix here. You can compare it even with the one from the instrument. So you see those two are really very, very similar, whether I do it on the instrument or in FlowJo. And then in order for the visualization, we have updated the platform. So basically, you can use here below, we don't have the n by n anymore, where we see each parameter versus each other, but we select a specific parameter and show that one. Yeah. So for example, oops, we'll go back here. Okay. For example, if you wanted to visualize here P Texas red, okay, I could select here from the list Texas red so that we show this parameter across all the different detectors with or not the uncompensated parameters. Okay, so here is how it was before compensation in yellow color, and in blue is the compensated values here. Okay. The nice thing about it is you can also highlight, so you can really click on a specific button here, a specific combination of fluorochrome detector, and this will highlight it in your plots below so that you can see how it was before or after um, compensation. Okay. In terms of the spillover spread matrix, it's the same thing. You can click on here. Okay, and you can investigate here cases where you have high spillover spread. For example, let's see at here APC size 7. Okay, we can see by APC size 7. Okay, so here is a value of 1.7 of spillover spread. Okay, so here is the spread you're seeing here. Okay, so this is not a particularly high. Okay, there is some spread, but I think it should be still okay for our analysis. And this is nice that you can highlight easily, okay, low values, high values, and see them directly on a plot below for your samples or your single stain controls. Okay. Right, so and then to apply a matrix to your samples, you simply need to drag and drop here from the matrices to your experiment data, and then you should have this matrix applied to your samples. Okay. So let's now do the following. Let's load also some spectral data. Okay. You'll see how similar everything is. So I'll do some unmixing here. We'll use our 20 single stain controls that we have here. So here are all of our single stain controls. And I'll press next once again. Okay. And again, what happens is we have the size gate, positive and negative for each single stain control. Okay. And we can choose whether we want to use the AutoSpill or the classic algorithm. Yeah, so here I have the AutoSpill on. Here it makes much more sense to look at the spectral plots, yeah, because you see we have all those different detectors here. And we can really see where our specific single stain controls has the highest emission in there. Okay, so in that case, I'll use again my AutoSpill on. I'll leave spectral. So I don't need to have any positive or negative gates in here. And if I have an unstained control, so here I see an unstained control. Yeah, I have this unstained control, and what I can observe from the, oops, sorry. Okay, what I can observe for my unstained control is where I have the highest autofluorescence. Anybody wants to type it in the chat box? Where do I have the highest autofluorescence in this unstained control? In which detector? So here are all the detectors. Any ideas? Yes, Isabel, correct. BUV450 is the highest autofluorescence channel here. So why don't I create a parameter here, name autofluorescence AF, and then assign right here. Okay, the channel that Isabel told us to. It's the BUV 450, this one. Okay. Okay, so all the rest controls I can check if I want manually or not. Okay, I can go through the rest of my samples. Maybe I have assigned somewhere else because I have assigned here. Okay, that's why you get this um, orange color. It's when you have any issues or when you have assigned the same detector for different controls. So I think here we have the wrong assignment of control. So here it should be V brilliant value 421. Okay, that should fix our problem. Um, that's great. AutoSpill on, spectral, and then I can proceed with my unmixing and press create matrix. Okay. Okay. So now the matrix is ready. I can preview it here. Okay. Or I can also go to my new matrix here. So the difference of here is instead of having a square matrix, we have all those columns here, which are all the detectors. Yeah, so that's, of course, editing this matrix is very hideous process, so it's not really easy to do so. Um, uh, because we have all those different detectors right here. But what we have for those of you that are actually doing, nevertheless, edit the spectral matrix, we do have for the unmixing correction applied in FlowJo, where basically we don't have any more parameter or control versus all the detectors, but we have parameter versus parameter. Yeah, and so in that case, you can actually make corrections, but without needing to check all of the different detectors. You can balance between two different fluorochromes. I can use an example here for BV 750, for example. Okay, here we have, for example, some overcompensation, okay, in this case. So now I can apply a value here. The values are between minus 100 and 100. Okay. Okay, we go here to unmixing correction, BV 750. So we can apply a value of minus 100 or 100, okay, which will is like really non-compensated. So maybe a value of 10. So the boundaries there are minus 100 and 100. Okay, so you can play around to edit this. Maybe 1. Okay, 1 should be enough. Yeah, so 0 look to be overcompensated. So we need to change the balance between those two fluorochromes. So 1 should be enough. Okay, so it should be great. So if you need to make those slight adjustments in spectral, very large rectangular matrices, the unmixing correction should be your go-to. Yeah, because you don't have any more all those different detectors. And once again, for this matrix, you can see also the spillover spread. So here we had, for example, a very large value for the APC. We can visualize it here. Where is that? APC. BV 650. Give me a second here. Okay, I don't see that very high value, but anyway. Okay. Sebastian is asking, can you transfer the scaling factors for the different colors? The scaling factors from the different colors from one matrix to another matrix. I don't really understand the question, Sebastian. Transfer the scaling factors for the different colors. You mean the heat map? How the values are heat mapped, or do you mean the scaling? Can you clarify? So the scaling for the different colors. Different colors. Maybe you mean different parameters. Yeah. So this, if you, yeah. So we do have the transformation version 11 is here. So we integrated this in the properties panel here. So once I make, for example, if I want to make transformation, I can transform my compensated, non-compensated, whatever I want here. For example, I can choose all my parameters, select by exponential scaling, width basis, positive, negative, um, and apply to all of my parameters at once. So, but from matrix to matrix, I'm not really sure if I'm honest. Like we did with drag and drop in version 10, right? So we could, um, I don't think it's possible. Thank you. Thank you, Sebastian. Okay, so that was it. I went a bit over time just to show you the software. But that was really it. Don't know if you have any other questions. Thank you all very much for joining. Um, I will look. I have something in the Q&A box. Yeah, somebody else asked about weight optimization. So we don't have that integrated yet in version 11, but I'll make sure to transfer this feedback and I'm happy to have it there for you. Okay. So thank you all very much for joining and see you maybe in the next webinar. Thank you. Thank you. Bye, everyone.